Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with lecture 1B, the second lecture of calculus chapter. So in the previous lecture we learned about standard functions, what are actually functions, okay, what is the definition of functions, and we saw a few standard graphs from there, okay, and yeah, those are important because if some basic question comes up right in gate examination, then you won't be able to solve those if you don't know the basic things. So those are also important. I know many of you haven't studied the basics. If you have, obviously you can watch this in 2x. So this also you can watch this in 2x if you have already studied the basics. Okay, this and the limits first lecture will you can also watch in 2x, right, if you are already accustomed with all of these concepts. But before starting this lecture, we have to solve the questions that I gave you in homework. So these were the questions, right? So I will tackle this modulus question later on. I will tackle these two questions. Okay. So this is very simple, right? Basically, for a straight line, you have to know two properties. Basically, its slope and its y-intercept, right? So what is y-intercept? Y-intercept is when my x is 0. So when is my x 0? X is 0. When is my x0? When I put my x0. So if I put my x0, y is equals to minus 1. Okay, put my x0, y is equals to minus 1. Okay, so minus 1, and its slope is positive, right? Positive, so hence it will be something like this, not like this. When slope is negative, the straight line is like this. When slope is positive, straight line is like this. Basically, this, what does this represent? This represents increasing. Slope positive represents increasing. As I increase my value of x, y should also increase. That is what this represents, right? And here it is 2. So if slope 1 is like this, then slope 2 will be like this. It will be more steeper. It will increase more faster because rate of change has increased, right? So it will be something like this. Okay. And what will my x-intercept? X-intercept will be when my y is 0. When is my y 0? When I make the y 0. So if I make y 0, 2x minus 1 equals to 0. So x equals to 1 by 2. So x will be 1 by 2 here. So let me just change these points. This is my this is 0 minus 1. And this is 1 by 2 comma 0. 1 by 2 comma 0, right? Okay, so this is my x and this is my this is my x intercept and this is my y intercept, right? So yeah, this is basically straight line. This is basically the plot of the first function, that is the 2x minus 1. Okay, and what is this? Basically, what do I call this? Y intercept equals to minus 1, and x intercept we have already found out. Only we need 2 points, right? 2 information we need, and that is enough. Sorry, I forgot 1 point. Yeah, we need, actually you can do it with slope also, or you need 2 points. So you can take x intercept and y intercept. Okay, for a straight line you need 2 points. Intercept. Okay, which is equals to 1 by 2. Okay, so yeah, that is it basically for this function. I will come to this function later on. Let's come to the third one, right? Let's come to the third one. So let me just copy this one up. Paste this. The third one is actually pretty interesting. We generally solve this using a method known as wavy curve method. I've already solved this in one of my, I've already explained this in one of my control systems lecture, so you can refer to that. Okay, or you can look it up in YouTube or somewhere else. What is a wavy curve method? So basically, right, wavy curve tells us about the what do you say, the sign of the function. Wavy curve method tells about the sign of the function when we have a factorized form like this, right? When you have factors, right? When you have factors basically. So what we do, we have to find out the sign of this, right? That is what I'm interested in right now, because like plotting this will be difficult for me. Plotting this exactly will be difficult for me. I will try to find the rough sign, whether this will be positive within certain range or negative, and after that I will plot the graph. Okay, obviously exactly plotting is not possible for me. That's why this is known as Wavy method. Why, I will explain. So basically, now what are the roots? What do you mean by roots? Roots is when this function is equals to 0. For what values of x this function is equals to 0, those values will be called as roots. Okay, those values will be called roots. Okay, now if those values is called roots, so this will be equals to this, right? This will be equals to, okay. And now what next? Now I will obviously mark the roots over here in this number. This is a number line, right? This is, let's say this is the number line, this is the x-axis. Okay, everything is recording, right? This is recording, and this is, yeah, this is also recording. This is my x-axis, right? So this is my x-axis. Okay, so I'm varying, I'm going from -1 is one of the roots, because x equals to -1 equals to 0, and then I have 0 also another root, and also I have 1 also another root, right? 1 is also another root. So if -1, 0 and 1 is also another root, then what does that means? That means basically at this juncture, right, the sign changes. Okay, all of this I've explained in my Wavy method. You can watch that video. Okay, so if you have studied contour systems, you will know. So basically now from where to start? I will start from the leftmost root. So I will try to find out what is the sign before this -1 point. Before I go, like I'm moving along this direction, okay, what is my sign before this -1 point, right? So just let me bring this more closer to me. So the sign before this, right, if my x is less than -1, x is less than -1, if x is less than -1, then obviously this part is overall negative, right? This part is also negative, because less than -1, -2 I can pick, which is negative, so this is also negative, and obviously this is negative anyways, we're subtracting, so this will be negative anyways. So these three, right, these three are negative anyways. So negative times negative times negative is what? Is a negative number itself. Okay, I'm getting a negative number itself. So I'm getting a negative number. That means that obviously for x lower than -1, right, I will get a negative. Right? Now for x higher than -1, what is happening over here? For x higher than -1, the sign will change. Okay, because I have got single factor, right? I have got single factor over here, the sign will change only once. Okay, if this was, let's say, x plus 1 whole square, then sign would remain same. Okay, that is important point. Obviously we have to check the overall sign also, that is also important. But if this one was x plus 1 whole square, the sign will change. But as this is e odd, right, only single element is present, only single factor is present, sign will change. So sign will change to this will be plus. Okay, and then what will happen? Then again we encounter at 0, again we encounter a root. Whenever we encounter a root, the sign again changes. Okay, the sign again changes. Again this will go on like this. Okay, this will go on like this, and again the sign will change as I encounter another root, and this time, right, sign will remain constant. Okay, sign won't change again, sign will remain constant. Okay, so yeah, this is the case. So basically this is -1, 0, 1, and these are my curves. So how will my graph look like? Roughly, right, roughly my graph will look something like this. I will explain. Roughly I can write it -1, this is 0, and this is +1, right? So roughly what will happen? Before -1, this will be negative, right? So this will be something like this. Just hold on a second. And around 0 it will remain positive. Okay, and after 0 again it goes to negative. Okay, and then again it is positive, right? It will go till infinity. So if it goes to infinity, it will be something like this. Okay, it will be something like this. And here also it comes back. It comes from negative infinity, so it will be something like this. Okay, as is the cubic equation, the graph will something look like this. Okay, now this is obviously a rough plot, this is not exact plot, but this is a good approximation what we can say, because in between this range, right, this will always be positive. Between this range 0 to 1, this will always be negative. Okay, and after this one, this will always be positive and it will go to infinity, and before this minus one, this will always be negative and it will go to minus infinity. Okay, so this is how my plot will be. So this is also another way to plot a graph. Okay, so yeah, this may not be that much needed, but this may be needed in signals and systems, also in some concept, right? This may be required. Okay, this skill may be required. So let's start with today's lecture. So first we'll start with functions and graphs. Whatever missing functions we couldn't cover in the previous lecture, we'll complete those, and obviously we'll end this with graphical transformations. So the first function is greatest integer function. So basically, what is a greatest integer function? Let's read the definition. Greatest integer less than or equal to x. So this is the symbol of greatest integer function. Okay, they will always mention that it is a greatest integer function if x is written in square brackets. Most cases they will always mention this. Okay, this is known as GIF. They may write in short form GIF, and the definition of this is greatest integer less than or equal to x. What do we mean by this? We mean that immediate previous integer, if x is not an integer, okay, anything else than integer, x is not integer, then it will be the immediate previous integer. Immediate previous integer. What do you mean by that? Let's say I have 1.23. Is this an integer? This is not integer. If this is not integer, I will take the immediate previous integer of this. Okay, the integer less than this. Greatest integer less than or equal to this. What is the greatest integer less than or equal to this? What is the greatest integer less than or equal to this? This is 1, right? So our greatest integer of 1.23 will be 1 only. Okay, basically this is known as a floor function. Okay, floor function, right? Why is this called the floor function? Because I'm ignoring the floor parts, right? I'm ignoring the floor parts. I'm ignoring the fraction parts. I'm only taking the integer part. Okay, that's why this is known as a floor function. Let's take another example. 1.87. 1.87. What will be the greatest integer of this? The greatest integer of this will be 1. Okay, greatest integer will be of this one, because I'm ignoring the floor. Okay, now let's take another great example. Minus 1.56. Now what will be the greatest integer of this? You might say I'll just ignore this floor and I will just take minus 1. You are wrong. The definition is this, right? Greatest integer less than or equal to x, or when immediate previous I will take the immediate previous integer if x is not equals to x, x is not equals to integer, and I will take x itself if x is equals to integer. Okay, so now the important point is here, is my x integer? No, x is not integer. So x is not integer, first point gone. So I will have to pick from this. I will have to pick the immediate previous integer. What is my immediate previous integer? My immediate previous integer is minus 2, not minus 1, right? Minus 1 is ahead of me. So in the number line, if I check, this is minus 1, this is minus 2, and minus 1.56 is lying somewhere in between. So minus 1 is ahead of me and minus 2 is behind of me. So I will pick the previous integer, not the integer in front of me. So obviously this will be the greatest integer of this will be minus 2. Okay, minus 2. So yeah, this is the point where students tend to get confused with the negative numbers. So need to clear this one up. Now next is, let's say I have 2. What will be the greatest integer of 2? It will be 2 itself, because it is an integer. If it is an integer, don't need to think anything. It will be directly x. Okay, so these two are the important points of the greatest integer function. So the graph of greatest integer function looks something like this. Okay, so you might see something like this is open circle, this is closed circle, this is closed circle, this is open circle, closed circle. So basically your open circle, right, these are denoted by open circles. And what do these represent? This represent that it will be excluded, right? It will be excluded. And what about closed circle? It's a closed circle. Closed circle. Will be basically the points which will be included. What do we mean by those? Basically, if this is open circle, right, so this is not included in the curve. So this 0, right, is not included at x equals to 1. So this point is included. So I'm suddenly jumping, right? So this point is included, which is equals to 1. So 1 will be included at x equals to 1, and it will not be included as this is a function, right? This is a function, only one point we should get only one point, that is with the vertical line test. That's why, right? That's why. Okay, so yeah, this is what we mean. This is included. So a closed circle means it is included, and an open circle means this is excluded. This point, this 1, right? Y equals to 1 is not included. This point is not included. We are including this point. Okay, so basically what, let's analyze this graph. So here, right, if I'm lying between 0 to 1, you can see my greatest integer function is always equals to 0, always, and that was expected, right? As I'm lying between 0 and 0 is also equals to 0 itself, and if I lying between 0 to 1, it will just cancel out the floor part, right? Cancel out the floor part, and I'll be only remained with this 0. If I lying between 1 to 2, it will always push it down to 1. Okay, whatever the value is, it will always push it down to 1, except when my x is exactly equals to 2, then I will suddenly jump off to 2 itself. Okay, so this is what this greatest integer like graph of this greatest integer function is. I don't think there is much explanation needed. I've already explained this very well. So another similar thing like greatest integer function is the fractional part of x. So what is the fractional part of x? Basically this is denoted like this third brackets. I don't remember what brackets these are called. So this fractional part of x equals to x minus greatest integer of x. Basically whatever the fractional part is left, right, that is the fractional part of x. That is what this name suggests. So let us take few more examples, and from there we'll understand. So let's say I have this 1.6, right, 1.86. now what will be my fractional part of x? My fractional part of x will be 0.86, right? My fractional part of x will be 0.86. because why? What is my, like, x is 1.86. what is my greatest integer function of 1.86? It is 1. It is 1. So 1.86 minus 1 is 0.86. that is what I am getting, right? Now let's take the negative example. From there you will understand this more better. 2.47. okay, now what will the fractional part of this? You will say 4.47. then you will be wrong. The fractional part of this will be 0.53, and it is always positive. Okay, fractional part is always positive, and it always lies between 0 to 1. okay, so fractional part always lies between 0 to 1. So this is one thing that lies between, because I am only taking the fractional part, right, and it can only lie between 0 to 1. Between, it is a fraction, right? Okay, so it always lies between 0 to 1. So it always lies between 0 to 1. What does that mean? So now I said you, right, it won't be 0.47. why? Let's use this formula. So this is minus 2.47, and what is the greatest integer of minus 2.47? It is minus 3. So this becomes minus 3. Minus into minus, it becomes 3. 3 minus 2.47. 3 minus 2.47 is 0.53. okay, 0.53. so that is why just be careful with negative numbers. Whenever there are negative numbers, just be careful with that. Okay, so it will lie somewhere around here, right? So if it is 2.47, it will lie somewhere around here. Okay, so no, it will lie somewhere around here. Okay, lie somewhere around 2.47 will lie somewhere around here, right? So yeah, I have got the point. It will always lie between 0 to 1, and this is the fractional part. There is nothing like fancy to this. Now next is modulus function. We already know this. We have already studied this previously, in our class. I mean in our school. So just giving you just a quite brief thing, that modulus function is represented like this: mod of x, okay, equals to this thing. So it will be equals to minus x when my x is lower than 0, so that it can make it positive. Okay, my modulus function will always lie above y-axis. okay, if I take the mod of anything, it makes it positive, basically absolute value. It makes it positive absolute value. It will make it above the x-axis, sorry, not y-axis, above the x-axis. So it multiplies a negative sign so that it can make this negative x positive. Then for 0, it is obviously equals to 0 itself. Then if my x is greater than 0, it will be x only. It will not change anything. So that is the definition of modulus x, right? So if y is equals to x, right? If y is equals to x, then the modulus of y equals to x will be this, because the negative portion becomes positive, symmetric about y-axis, symmetric about it flips this to y-axis, and my modulus function is always symmetric about y-axis, because this is the even function. This is the even function. Okay, because if we simply do f of minus x, you will get the same function back again. Okay, f of minus x and f of x will be same, so that's why this will be even function. So this is an even function, and this is symmetric about y-axis. It will be symmetric about y-axis, right? So that is one thing. Also, any other things you can notice. You can notice that if my y is equals to x, right? Y is equals to x, then there is a very sharp turn around here. There is a very sharp turn around here. Okay, and this is important in the differentiability chapter, not here, in the differentiability chapter. Okay, sharp. Okay, sharp turn. So yeah, this is the case basically. So now, right now, function sharp turn. Okay, let's solve the quotient. Okay, like there is another definition for mod of x. Basically, mod of x can be written as maximum of plus x and minus x. So like whatever is inside this modulus function, I will keep this as it is and then multiply a minus 1 sign with it. Now whichever will be maximum out of those two. For a negative number, let's say minus 1. For minus 1, what is maximum? Minus 1 or minus 1 into minus 1 plus 1. So plus 1 will be maximum, so I will take plus 1, right? So basically it makes the negative value positive. Okay, that is what this does. So obviously here what will happen, these, right, these, like this is what, this is y equals to plus x and this is y equals to minus x. So basically this, right, this and this I can cancel out, this and this I can cancel out, right? This and this I can cancel out. If this and this I can cancel out, then obviously I will be only left with this, okay, which is I got in the previous case. Okay, which is I got in the previous case. So yeah, let's like solve quotients of the modulus function, then I will come back to this. Okay, then I will come to the next part. So yeah, this one was the graph, right? So what do I have to do for negative values of y? So what do I want to do? Basically I want to plot the modulus of this, modulus of 2x minus 1. Okay, so you try to do it by yourself. Basically what does modulus function does? A modulus function basically makes the negative values positive. That is what the purpose of a modulus function is, right? So the positive values will remain as it is, will not do anything with them, but the negative values I will just multiply a minus 1 side with it, so that whatever the value, magnitude won't change, but the sign will change. It will become positive instead of negative. So I will just copy this graph. Okay, copy if I can. This whole feeling very sleepy. Okay, so let me just color this differently. So here, right, so which portion is negative? This portion, right? Obviously what is the negative portion here? This portion, right, where my y is negative, this portion is negative. I just need to flip it from this point, so that this also becomes positive. Okay, and all the points will remain same. So this will be something like this. It will flip it over, right? It will flip it over. Okay, so yeah, this is basically this point. These are basically this points, right? These are basically like this is the modulus of that. So this is how we plot this. Okay, I hope we got the point. Basically this is just flipping the negative portion in the positive portion. All the values, magnitude will remain same, just the sign will interchange. Now this, instead of being minus, will become plus, right? It will become plus 1. Okay, it will become plus 1. So yeah, that was the plot. So let's now continue with our functions. So next, what is next? Next is a key point to again define the ranges. So we can write the ranges using the closed interval, open interval, that format also, using this format also. How? Let's say if my x is lying between -1 to 1, x is lying between -1 to 1, how can we represent that? So basically I can represent it in a single format, that is my mod of x will be less than 1, not equals to less than 1. How can we say this? So this mod of x includes both -1 and 1. Okay, this mod of x includes both. How? Basically, if I write mod of x equals less than -1, what does this represent? If I put x equals to -0.5, if I put x equals to -0.5, and x equals to 0.5, right? Are these two, the mod of x values for these two are same, right? These are satisfying. Okay, so this will satisfy. So again, this is lying in this range, -0.5 and 0.5 is lying in this range, right? Now if I pick x equals to -1.5 and 1.5, plus 1.5 and -1.5, so again mod of x will be 1.5 itself, so which is not satisfying, which is okay, right? So like this you can understand, right? So this one single mod of x including this -0.5 and 0.5 also, so negative and positive is including both. So if something like this is written, so we can write it like this, or something like this is written, this represent this, right? So you can go both ways. Now if I write x is varying from -1 to 1, okay, I have made a mistake, it should be equal over here, right? This should be equal over here. Now if this is equal, obviously the difference will be mod of x will be less than equals to 1. Okay, mod of x will be less than equals to 1, right? Now if x is greater than 1 and x is less than -1, if x is greater than 1 and x is less than -1, what does that mean? That means that here this is union. Okay, x greater than 1 or x less than -1. Okay, so what does this mean? This means that it is going towards -infinity it is going, and this is going towards +infinity, and it is greater than 1. Okay, so 1 to -1, this range, right? This range is not included here. This range is not included. This range was previously included, now this range is not included. This range is excluded, right? So how can I write it? So basically what I can write, if my mod of x is written like this, that what do I have to think? So I have to exclude -1 to 1. I have to exclude this. Okay, everything else is included. So I will just do the opposite of this. So I can write mod of x greater than 1. So if I write mod of x greater than 1, what does happen over here? So if I write mod of x greater than 1, basically I'm including 2 points, -1, 1, -1.5, 1.5, -2.5, 2.5. So yeah, those are true. Okay, for x equal to -1.5, this equation is satisfying. For x equal to 1.5, this equation is satisfying. For x equal to -2.5, this inequality is satisfying. For x equal to -3.5, this inequality is satisfying. For x equal to 3.5, this inequality is satisfying, right? So for x equals to -0.5, this inequality is not satisfying. That's why my x can't be -0.5, which is fine because we are not including this range. Okay, so again you can write it like this. Basically the opposite of this. Again, if we're including x and -1, the slight difference will be mod of x will be equals to 1. Okay, that is just the simple thing. I won't go much deeper into this. Okay, so next is the Signum function. This is mainly used in signals and systems, and this is also known as sigmoid function, right? Sigmoid function. Okay, that is very important function in artificial intelligence. So if you study about that, you will understand. So it is also known as sigmoid function. Okay, also it is known as sine function. If I am able to write this, also it is known as sine function, right? So I have sigma. This is Signum of x, and this is like defined. If x is positive, it is equals to +1. So here, right, if x is positive, it's equals to x itself. But if here x is positive, it is equals to +1. It's just gives me the sign. If x is equals to 0, it will give me 0, so it has no sign. If x is negative, it will give me -1. So it will tell me the sign of the value whatever is inside this Signum function, right? Whatever is inside this Signum function. So if y is equal to Signum of x, basically this is open circle, right? So at x equal to 0, it is not equals to 1, it is not equals to -1, it is equals to 0 itself. That's why these are open circle and this is closed circle. Okay, now if x is greater than 0, obviously it is positive number, so it will give me output as 1. If x is less than 0, obviously it is negative number, it will give me output as -1. Okay, -1. Okay, now what is the alternate definition of Signum of x? What is the alternate definition of Signum of x? Okay, so basically Signum of x equals to x by mod of x, right? X by mod of x. You can define it for yourself. Basically this, right? This modulus of x, what does this does? It makes it positive always. It always makes it positive. And here, right, if x is positive, this will be x only. If x is negative, this will be something -1. So let me give you example. So let me take -1. So if I take -1 over here, in the numerator there will be -1. In the denominator there will be +1 because it makes it positive. So -1 by +1 is 1. Then again, let me take another example. -5. So if I take -5, in the numerator there will be -5. In the denominator there will be 5. So -5 upon 5 is -1. So we get the sign. Basically we only need the sign. That's why I'm dividing by x itself, but the modulus function helps us in decoding the sign also. Okay, so you can use this. Obviously if x is equals to 0, we can't divide by 0. Okay, why? It is an undefined value. That's why x is not equal to 0. If x is equal to 0, we directly define Signum of x is 0 itself. And the same thing for this one. Okay, I won't go too much into the details of this. Okay, so these are the few questions. What I will recommend you to do is take this as homework. Plot the following functions. Okay, the Signum of x, the greatest integer function of this sin x, and the Signum of this, right? We have already plotted this previously, and sin x we know, you know already, I hope. If you don't, we are just studying in the next few slides the trigonometric functions. You can see from there. I'm giving you all this as a homework, right? All this as a homework. Now let's understand the trigonometric functions. So what are the trigonometric functions? Trigonometric functions are the sine function, cosine function, tangent function, cotangent function, okay, sec function, cosec function. Then we'll study about the inverse trigonometric functions. Okay, so sine, everyone knows. Like all of you are mostly all of you are from electrical background. Our students are mostly from electrical background. So sine, I hope you already know this. Okay, sin x is something like this. Okay, it is not a polynomial function. And also, what type of function is this? Is this an odd function or even function? As you can observe, right, it is symmetrical about the origin. If it is symmetrical about the origin, this will be odd function. Okay, this is equals to sin x. Okay, and it is basically odd function, right? It is basically odd function. It is basically odd function. So this is a odd function, right? Okay, so also, like, what is the period of this? This is a periodic function. What does a periodic function mean? Periodic function means whichever repeat itself after a certain time. So let me just quickly write a few things. So periodic function, right? It repeats itself after a certain period. So all these right trigonometric functions are periodic functions. Here you can see that it is repeating after every 2 pi. So 2 pi is radians. This is in radians, right? So I hope we already know this basic things. So 2 pi is in radians, and this repeats itself after every 2 pi value, right? 2 pi value. Now what are the points to note over here? The points to note over here is what are my zero crossing points? What are my zero crossing points? So my zero crossing points are this, right? Minus pi, 0, pi, 2 pi, all these are zero crossing points. Okay, so basically it is a integer multiple of pi. It is an integer multiple of pi. So what are my zero crossing points? So zero crossing points are sin x equals to 0. So x equals to n pi, or for all n, right? X equals to n pi for all n, okay, where basically my n has to be integer. Okay, I should write this for all, right? For all, I should write here for all x where my n is basically integer, right? N is integer. Integer is represented like z, and like basically it will be 0, 1, 2 and so on, right? It will be 0, 1, 2 and so on. Okay, so this is what my n is. And also another important one note here is that my sin x function will always lie between -1 to 1. Okay, it will always lie between -1 to 1. Okay, and it is oscillatory in nature. Okay, it is never settling, because as we increase x, there isn't any constant value. It is never settling, it is oscillatory in nature, right? So my sin x will always lie between -1 to 1. Okay, this is also another important point. Okay, next is cosine of x, basically cos x. If you remember cos x, now like this is equals to cos x, f of x is equals to cos x. And what type of function is this? What type of function is this? This is a even function, right? Even function, because this is symmetrical about the y-axis, not about the origin. Symmetrical about the y-axis, right? Like as you can see, right, if I split it into two parts, this and this part will be same, right? Same only. So this is symmetrical about the y-axis, and obviously my cos x will also lie between -1 to 1. -1 to 1, right? My cos x will also lie between -1 to 1. Okay, so this is the case. Next is tangent of x. So what is tangent of x? So tangent of x can be written also as sine by cos, right? Sine by cos. So tangent of x, I can write, use some other pen. Okay, so my f of x equals to tan of x. So again, right, what is this? Is this even or odd? You can see, right, if I break this down about the y-axis, this is not same again. But if I see about the origin, I can see this is going in this direction, this is going in this direction, and they are about symmetrical, right? So obviously this is an odd function. This is an odd function. You can prove it with the mathematical proof as well, whatever mathematical relationship I have given you, right? So but like we can observe from the graph itself, this is an odd function. Okay, this is an odd function, right? So this is an odd function. And what is the period of this? So this period, right, this has the period of 2 pi. This has the period of 2 pi. Again, what are the zero crossing points? The zero crossing point this time are not n pi anymore, they are n pi by 2. So I will explain those, just hold on a second. The period of this, right, two pi. The period of this is 2 pi. And what are the zero crossing points? This time the zero crossing points are different. Oh no, I wasn't able to copy. Cos x equals to 0. So if cos x equals to 0, that means basically my x has to be n pi by 2, right? So if my x is n pi by 2, okay, and also it can't be, okay, what am I missing over here? N plus 1 pi by 2. I can write yeah, n pi by 2, this is 3 pi by 2. Yeah, fine, but this can't be 2. Previously did I do something wrong over here? No, these are only pi only, right? Yeah, pi minus pi. Okay, it can be negative as well, sorry. Okay, it can be negative as well, I missed this point. -1, and like from minus infinity to plus infinity, all of them are integers here, right? So yeah, that is this. And what about this? I can't simply use here integers. I have to use what? I have to use odd integers. I have to use odd integers, right? So how will I use odd integers? That is what I'm saying. So there will be 2n plus 1. So I should write this like this. So these are all odd numbers. So even if I pick something, right, like this, they will still be odd, because n equals to 1 is 3, n equals to 0 is 1, right? So all of this will be odd only. Okay, so x is 2n plus 1 pi by 2, n belongs to integer, this, right? N belongs to this. Okay, and like yeah, these are the zero crossing points for a cos function. So only the odd multiple of pi by 2, only the odd multiples of pi by 2. Like this is also another thing, these are basically the even multiples of pi by 2, even multiples of pi by 2, because 0, okay, or you can say pi, even multiple pi by 2, 2 times pi by 2 is pi only, right? So I can like see here in words even multiples of, like I can further express this, right? I can further express this like this, 2n into pi by 2, the same thing, and like 2n will be always a even number. So this is known as even multiple of pi by 2, even multiple of pi by 2, and this is known as odd multiple of pi by 2. Okay, so this is how also you can say this in words. So let's come back to the tangent function. Basically, what are these? These are asymptotes, basically plus infinity and minus infinity. So these are asymptotes. Asymptotes we have already learned in Bode plots, I hope. Like asymptotes we have already learned in Bode plots, right? So these are asymptotes, and this is f of x, and this is tan is equal to sin x by cos x. Okay, and this is odd function. All this we know, and this is a ratio between sin x upon cos x. So if you just put this pi by 2, right, at pi by 2 what happens? My cos x goes to 0. It is basically odd multiples of pi by 2. So cos x goes to 0. Now what is my value of my sin? For minus pi by 2 it is minus 1. So that's why it tends to go to minus infinity. Okay, minus infinity. But just here, right, just here if you observe, it tends to go to plus infinity. So let me take the 0 example, x equal to 0. So not sorry, okay, we can take x equal to 0. We have to take this only. So if I just before minus pi by 2, it is going to plus infinity. Just after minus pi by 2, it is going to minus infinity. Why is this the case? This is the case because my cos pi by 2, my cos pi by 2 is what? So here, right, just before it is negative, just after it is positive, right? Sine is not changing its sign, basically. Sine at pi by 2, right, it is always negative. It is always negative. Sine pi by minus pi by 2 is always negative. So just after this becomes positive. So if this is become positive, so negative upon positive is something negative itself. So I'm getting negative just after minus pi by 2. Just before minus pi by 2, my sine is negative, but my cosine also becomes negative. So negative upon negative becomes positive, and cosine is very small number, very small number. So something constant divided by very small number tends to infinity. So this is tending to positive infinity. So just before this and just after this, in the neighborhood of minus pi by 2, the two values are not equal. Why am I stressing this much? Because this is important. This will come in handy. Okay, so yeah, this is one thing. And what is the period of this? The period of this is only pi. Okay, because this is repeating from pi by 2 to 3 pi by 2, you can say, or from this 0 to pi, you can say, right? So the period of this is pi, not 2 pi. That is important. The period of sine, like period of this, right? Period of this is the period. This is the period cosine, and the speed of tan is only pi itself. Okay, period of sine is pi itself. Okay, so yeah, this is the thing that I wanted to say. Now, like these are the things we will learn more about this in the limits chapter. Okay, in the limits chapter. But what are my zero crossing points? What are my zero crossing points? The zero crossing points will be basically whenever my sine crosses 0. Okay, so whenever my sine crosses 0, it will also have zero crossing points. So basically, it will be ditto same as this. Because cos x anyways at that point of time is non-zero, so it doesn't matter. The denominator 0 should not come. That is the most important part, right? So basically, I'll just change one thing. My tan x has to be 0. For tan x has to be 0, sin x has to be equals to 0. Okay, so sin x has to be equal to 0, and like from there you can further solve this. Now let's come to the cosec function. Just hold on a second, I have to drink a bit of water. Yeah, sorry. So just a bit tired. So let's come to the cosec function. What is cosec function? Cosec is basically 1 over sine. It is 1 over sine x, right? So it is the like the inverse of this, reciprocal, not the inverse, reciprocal of sine x. So it is reciprocal of sine x. So what can we say? That if my sin x is odd function, then my cosec x will also be odd function, right? As we can observe from here also, because it is symmetrical about the origin, so it will be an odd function. Okay, it will be odd function. Okay, so my sin x varies from what to what? Sin x varies from -1 to 1. So it takes all of the points, at all of the points -1 to 1, that also includes 0. So if sin x is varying from -1 to 1, then what will my cosec vary? It will vary from -1 to infinity, because 0 is included, right? 0 is included. So -1 to -infinity, +1 to +infinity. So it can vary like that. So here this is +1 to infinity, +infinity. Then this is -1 to -infinity. I have got the point, right? So like I'm not explaining this further, this will just waste our time, so I'm not just wasting our time, right? So further these things you can do it for yourself, like observe for yourself. I'm just showing you the graphs. What is sec x? Now what is sec x? Sec x is 1 over cos x. 1 over cos x. Now if it is 1 over cos x, the period will remain same here, right? The period will still remain same, right? Period is still 2 pi, okay, because sin x has period this, and this also will have same period, right? This will also have 2 pi, okay, but as cos x is even, this will also be even function, symmetrical about the y-axis, okay, symmetrical about the y-axis. Further things you can like do it for yourself. Then what is cotangent of x? It is basically cot x, and cot x is basically equals to 1 by tan x. Cot x is basically equals to 1 by tan x, right? Cot x is basically equals to 1 by tan x. So it is equals to 1 by tan x. So basically, right? Basically, what is the period? Period for this will also will be same only. It will be equals to pi only, right? It will be equals to pi. It will be equals to pi only. Okay, so f of x is cot x. Okay, so basically what next? So these are the asymptotes we already know, and like my tan x is varying from -infinity to +infinity, so cotangent will also vary from -infinity to +infinity, because 0 is also included, -infinity is also included, so 0 will also come along here. Okay, so I'm not like explaining these things, you can understand this by yourself, right? So let's go to next few things, right? Next few definitions. So what do you mean by undefined value? Undefined means we can't define those things. Can you define infinity? What is the value of infinity? What is infinity? Can you say? I might say infinity is 10 million, 10,000 of million, 10 billion, billion. Okay. So I can't define infinity. That's why it is called as undefined value. So how can I like express this undefined value? Can I express this? So like tan x, right? Tan x or cot x is going to infinity. So like if my f of x, if my example, if my f of x is equals to tan x. Now can you tell me what will be my f of pi by 2? What will be my f of pi by 2? It is equals to positive infinity, if you recall correctly. If you recall correctly, you just put the value of pi by 2 in your calculator anywhere. Okay, anywhere you put pi by 2, tan of pi by 2, you will get undefined. Okay, so basically this is known as undefined value. But can we quantify this? So how can we quantify? We can quantify like this, that I have, let's say, anything at the numerator, 1 I can take anything I can take at the numerator, and below 0. Now this is not exactly equal to 0. This is tending towards 0. Okay, from the positive end, 0.0001, 0.0001. Okay, so if my 0 is very small, 0 is very small, right? If my 0 is very small, basically let's say this is 0.01, okay, or this is 0.000001. What will be the value? It will be very large, right? It will be very large, okay, because this is in the denominator. So you reduce it further, you try to go more closer towards 0, you will almost reach infinity, but you can never touch it. Okay, you can never feel it because it is undefined, it is not defined. Okay, so yeah, I have got the point about the undefined value, and this concept, right, this concept will be used in limits. We'll go to limits, and from there we'll understand. Now what is oscillatory value? Oscillatory value means it is finite. Here that this was infinite, it is finite. We can quantify that 2, 3, we can quantify those things, but it is uncertain. What do you mean by that? So like let's take an example. Let's take an example. If f of x equals to cos of 1 by x minus 1. Okay, f of x equals to cos of 1 by x minus 1. Okay, then now what will be f of 1? So this, right, this will be cos of infinity with something very high value, which is never stopping. Now what is cos of infinity? Like this is x equals to 1, right? This is 1 over 0, which is tending towards very high. Now let me come back to the cos graph. Now this cos, right, this is the x-axis, and this, if I move more towards right, the more I move, that it will more move closer towards infinity. Obviously I can never reach infinity, but it will move more closer towards infinity. Now I am moving more towards right, and this is also varying, right? This is keep on varying, right? So I don't know what is the value of that. I don't know where I will stop, because I'm moving more infinity and I can never touch the infinity. I'm moving on the right hand side, but I can never touch it. I will never stop, basically. I will never stop. So this is like this only, okay, and this graph is like this. So, but what is the important point? One thing sure I know, that it has to lie between +1 to -1. It will lie between +1 to -1, but I don't know where exactly it will lie. But I know like it will lie between these 2 points only, because I'm always moving on the right hand side. So I'm moving along this curve, right? So it cannot go beyond +1 or below -1. So that is what I know. So so from this expression, right, what I can conclude? I can conclude that this will lie between -1 to +1. That is for sure. But where it will lie, I don't know. So this is oscillatory nature. Okay. This is oscillatory, right? So this is the case. Now let's like these 2 points I wanted to give you a quick feedback of. Now let's come to inverse trigonometric functions. Okay, so trigonometric functions are many to one, so the inverse cannot be determined. Okay, so basically What do you mean by this? So what is the point here? So like let's say I have a y equals to sin x, right? Y equals sin x. What does inverse mean? Inverse means basically if I take the inverse of this, my x will be equals to sin inverse y, right? Okay, x will be equals to sin inverse y. That is the main point in inverse. If I take the inverse, right? So x and y, I'm taking the inverse of sine. So I'm taking inverse trigonometry. So x will be equals to sin inverse y. So my x will be angles and y will be basically my output, input, right? Y will be input this time. So if I say y is equals to 1, what will you say to me? If I say y equals to 1, what will you say to me? So what is sin inverse 1? Sin inverse 1 can be what? Let's go to the graph here again. So if I see, when is my sin 1? Sin is 1 here, minus 3 pi by 2. Sin is 1 here, pi by 2. Sin is 1 here at 5 pi by 2. Okay. So sin is sin is 1 so many times, right? So many times. So what will be your answer? Because if I want to say what will be sin inverse 1, what will be sin inverse 1, right? So what will be my sin inverse 1? So basically you can say it can be pi by 2. Every 2 pi it is repeating, right? It can be 5 pi by 2. It also can be minus pi by 2. All those things it can be, right? But what is the problem over here? I can only get one output, right? But I need only one output, because for a valid function, for a particular input, this time, right, y has become input, right? So very important, don't get confused. So this is my output and this is my input, but as soon as I take the inverse, this becomes my output and this becomes my input. Okay, so here, right, I for a single input, I am getting multiple outputs, okay. So for a single input I am getting multiple outputs. That is very important, right? So this can't be function, because the definition of function was for a single input I should get a single output only. Okay, the output can be same for different inputs as well, that is fine, but I should get a single output only, not multiple outputs. So not function, can't be called a function. Can't be called a function, right? Can't be called a function. Okay, so yeah, this is the case basically. So that's why, hence we have to restrict our domain so that function is one-to-one within that domain. Okay, what do you mean by this? So if I restrict that, this, right, y, I can give only basically this x, right? If I restrict the domain of this x, like I'm talking about this function now, if I restrict this to 0 to 2 pi, if I restrict this to 0 to 2 pi, then what, or like minus pi by 2 to pi by 2, whatever you choose, like one period only you should choose, because this is repeating, right? This is every time repeating. So if I just choose one period, I'll be able to exactly have a one-to-one mapping. So right now, if I can say I'm restricting my domain from minus pi by 2 to pi by 2, so then what will be my value of sin inverse 1? You will say it will be equals to pi by 2 only, because I can only give pi by 2 input to this initial function, right? Initial function I can only give pi by 2. It will pi by 2. So if I say what will be my sin inverse 0, it will be 0 only, because I am restricting my domain to minus pi by 2 to pi by 2, right? Minus pi by 2 to pi by 2. Okay, here I explain this in short. Okay, you can see, right, I am restricting my domain. Okay, because as you can see, like if I just don't restrict my domain, then what will be sin inverse of 0? It will be even multiples of pi by 2 or integer multiples of pi. So at pi, 2 pi, 3 pi, 4 pi, these will be my solutions for sin inverse 0. But obviously that is not possible. There has to be like one input can only map to one single output. It cannot map to two outputs, right? That is not possible. That's why we are restricting our domain. Here we have restricted our domain so that when we take the inverse, we will get a 1-to-1 mapping. 1-to-1 mapping, right? 1-to-1 mapping. I hope you got that point. You just search one-to-many mapping. One-to-many means for a single input, I'm getting multiple outputs. Many-to-one, that means for many inputs, they may map to the same output. That is fine. Okay. For f of minus 1 equals to 1, f of plus 1 is also equals to 1. That is fine. That is not an issue. Okay. Vertical line test, right? Remember vertical line test. But for this one-to-many, that is a problem. For a single input, I'm getting two outputs. That is a problem. So that for the to avoid that, we are restricting our domain. So these are the domains for the trigonometric functions. You can go through this, right? And yeah, that's why, like, obviously we know that x can vary from minus 1 to 1 only, because I'm taking the inverse this time. So sine can only vary from, sine x can vary from minus 1 to 1. So like the inverse, the whatever we can vary, right, from minus 1 to 1. Also we have restricted our output also from pi by 2 to minus pi by 2. Here also it is restricted from 0 to pi. Okay, so you can just check the graphs. Okay, I won't go too much in depth to this graphs. You can just check the graphs for yourself, and this will help you quickly revise everything. You can understand that how is this coming, that you have to understand for yourself. Okay, next is the exponential functions. So exponential functions are there are two things. One is when, like, it is a raised to power x, when my a is between 0 to 1, and when my a is greater than 1, right? A is greater than 1. Okay, so basically if my a is between 0 to 1, what happens over here? So let's say I'm doing minus 0.1, right? 0.1, not minus 1, 0.1 whole square. So if it is 0.1 whole square, this is x, right? This is x. So if it is some positive value, this will reduce it further. So whatever my value of x is, right, it will try to reduce it further. So this raised to power 0 will be 1, and after this, right, after if I increase this raised to power 1, this is 0.1, this raised to power 2, this is 0.01. So this is reducing. So this will always be lower than 1. This will always be lower than 1. Okay, and up here what is happening? If I write 0.1 raised to power minus 1, this means 1 by 0.1, this is 10, right? So this is 10, this is always greater than 1. So that's why this left hand side will always be greater than 1. This is my x. Remember, this is my x, right? This is my x. Okay, so this left hand side will always be greater than 1, and this right hand side will always be lower than 1. If my x is, obviously, if x is positive and my a is lying between this range. Now for this case, right, for this case, what is happening? If my a is greater than 1, that means that let's take 2, right? Let's take 2. Now if x is positive, okay, if x is positive, let's take 2, it becomes 4. Fine. So it will be always greater than this 1, right? So basically when x is 0, it is 1. Okay, it is 1. When x is 2, it is 4. And if I further increase it, it will further increase, right? Now if I decrease my x, so if I decrease my x, what will happen over here? So this will be 2 raised to power minus 1. So this will be 1 by 2. So this will be 0.5, right? This will be 0.5. So this will be less than 1. So that's why on the left hand side, this is always lying, this is always below 1, and on the right hand side, this is always above 1. Like this, you can understand. Obviously, like this is going towards 0, okay, because this is less than 1, and if I increase it further, this will go towards 0, and this will go towards infinity. Okay, so these things you have to keep in mind. And for log, right, for log, these are just opposite of these things. Okay, these are just opposite of these things. What is the important point over here? What do we mean by log? So basically this f of x is the power, right? Basically if I want to write this in a more like a accustomed manner, we can write it like this. So this is this a raised to power y equals to x. This is what this equation represents, right? This is what this equation represents. Now if my a is between 0 to 1, what will happen over here? So if my a is between 0 to 1, so a is between 0 to 1, so let me take one example of what time is it? Of this 0.5, right? 0.5, and if my x is greater than 1, this is y, x is greater than 1. So obviously y has to be equals to 0 this time. Y has to be equal to 0, which is fine. Y is equal to 0. Now if my x is greater than 1, let's say this is equals to 4, right? If this is equals to 4, what can solve this equation? So my y has to be negative, right? Because this is 0.5. This 0.5, I have to make it reciprocal. So this becomes plus 2 or 2 square. So this has to be 2 square, right? So basically y here, right, will be equals to minus 2, right? Minus 2, because I have to like make it reciprocal as well, because I have to make it more than 1, okay, to bring it back to 4. So that's why this graph is negative after y equals to 1, and that's why this graph is positive after y equals to before y equals to 1. Why? Because this value right here, if I write this 0.5 y equals to, let's say my output is 0.5 itself, okay, not 0.5, I won't say 0.5 because y will become 1, which will be positive again, which is fine. I can say 0.25, right? So if I want to say this is 0.25, what will be this? This will be 2 y square, right? So this will be 0.5 square. So again this is positive. So before 1 this is positive, after 1 this is negative. And similarly, like the same thing you can decode it for this right hand side graph as well when a is greater than 1. Okay, I won't explain this again. So few definitions we have. Also, like this, right? Obviously I won't plot for negative value. So my domain, right, domain of x will be only for positive values. Why is this the case? Why is this the case? Can you tell me? X belongs to 0 to infinity. Zero also I can touch because this is anyways 0, so 0 I can touch. Okay, 0 to infinity. Why is this the case? If you observe this here correctly, right? If I observe this here correctly, this time my y is the output. So what is my range? My range becomes domain here. What is my range? It is between 0 to infinity. 0 to infinity because it is going to 0 and infinity. So the range becomes domain here because log and exponential are just inverse of each other, kind of inverse of each other, right? That's why. So here, right, I will always get between 0 to infinity. That's why the domain becomes 0 to infinity here. I have got the point. Okay, so now let's read few key points. What are the key points? Key points is if I replace my y to minus y, and if the function remains same, it will be a symmetrical function, symmetrical about x-axis. So basically so let me take an example. Let's say I have y square equals to 4x. I have y square equal to 4x. So if I have y square equals to 4x, now if I change my y to minus y, what will happen? Nothing will happen. Okay, nothing will happen. Equals to y square equals to 4x. I get the same equation again. So hence this will be a symmetrical function about x-axis. If you plot the graph, this will be symmetrical about x-axis. We know the graph was something like this, right? So it was symmetrical about the x-axis, even though it was not a proper function. Okay, but the curve was symmetrical about x-axis. That is more important to us. Okay, next is this, right? Next is this. If we replace x with minus x and the function remains same, it will be symmetrical about y-axis. Basically, this is a even function. So this will be symmetrical about the y-axis. This will be even function. Okay, and what else? Like let me give you an example of even function. X square equals to 4ay, just like simple parabola, right? Like here, like this. So it was symmetrical about the y-axis. Next is if I interchange x and y, what will happen? If I interchange my x and y, what will happen? If the function remains same, then it will be symmetrical about the y equals to x line. So what is the example of this? The example of this, you can take y equals to 1 by x, the rectangular hyperbola. Okay, now the rectangular hyperbola was something like this, right? This and this. Now if you plot the y equals to x line, you can see that it is exactly cutting those into two halves, right? They are symmetrical to each other. So you can say that yeah, it is symmetrical about y equals to x line. So these three key points you have to like remember. These are not that heavy to remember. This you can understand intuitively as well. Okay, now what are graphical transformations? So what are graphical transformations? Graphical transformation is basically equals to y equals to, like y equals to fx is there. Now I am making some transformations with it. Okay, what type of transformations? Basically, if my y dash, like I'm changing my function, I'm adding the previous function with plus minus a, what will happen? It will either shift up or down by a units. Okay, with a units, right, the previous function. So if y is something like this, okay, if I add a units with it, it will become something like this. Just copy this and paste this, and it will either shift it up, okay, and I will color this to different thing, okay, or shift it down. Okay, so either it will shift it up or shift it down. Okay, next is another thing, if I basically I'm not directly adding with the function, I'm changing the x value. I'm changing the x value, manipulating the x value. Now if I manipulate the x value, then it will shift left or right by a units. Basically it is a horizontal shift, right? So if I just copy this graph, it will either shift it here, okay, and either shift it here. So I should write this a units here. Okay, a units. So like here also, I should change the color of these things. So let me mark this green, let me mark this, and this will shift, like this will shift, right, this and this again, a units. Okay, so yeah, left and right on the a units. Okay, so this is known as the horizontal shift. Now if I just directly multiply a minus 1 with this, obviously it will reflect around the x-axis, because whatever positive things were here, it will become negative, and whatever negative things were here, it will become positive. So it will simply reflect about x-axis. So basically what will happen, copy this, okay, so it will basically reflect, right, a reflection. Okay, it will be a reflection about the x-axis. Okay, so next is y is equals to f of minus x. Y is equals to f of minus x. So basically if I, like, now I am not multiplying minus 1 with the function, I am just multiplying minus 1 with the x, right, with the independent variable. So it will reflect about the y-axis this time, because whatever for positive x values I was getting this graph, right, I will get the same thing for negative x values, and for negative x values whatever I was getting this, I will get for positive x values. So basically it will reflect around the about the y axis. Okay, so I will just plot this thing, it will be same only. Okay, and what will this graph be called? This graph will be called y equals to e raised to power minus x. Instead of x I'm writing minus x, right? So yeah, it will be simply symmetrical about the y. Yeah, actually my storage got over, that's why I had to restart this thing. So this graphical transformation you understood, I hope. Next graphical transformation is basically scaling. So if I am simply scaling, right, with a, okay, I'm multiplying the function with a, either it can stretch or compress. If a is greater than 1, it will stretch. If a is less than 1, it will compress the thing. So let's say I have a sin x, right, this is equals to sin x. So this, right, this is equals to sin x. Now if this is equals to sin x, then what next will happen? Basically if my a is let's say 2, if my a is 2, so it will be 2 sin x, so it will stretch it. So what I will do is I will first write these things. Okay, so the graph will look something like this. Okay, I won't be able to exactly plot it. The graph will look something like this. Okay, and what about this? So here, right, this is simply 2 sin x. So my a is greater than 1. If my a is greater than 1, I am getting expansion, I'm getting stretch. Okay, I'm getting stretch. Now when will it compress? So it will compress when my a is less than 1. Okay, obviously a has to be positive also, that is also important. So these things you already know, just quickly giving you quick revision. So here, right, this is, let's say, 0.5 sin x. So here, right, a is less than 1, but the important fact is a has to be greater than 0, a has to be positive. Okay, a has to be positive, right? So these are a few important points. So this is one graphical transformation. Now instead of directly scaling the function, I'm scaling the x, right? So basically I'm scaling the axis. So my axis will be scaled this time, stretch or compress about the x axis. So my axis will be stretched. So what will happen, right? So if my, this is sin x, right, this is sin x. So if this was, this is sin x, so just hold on a second. This 0, this is pi, this is 2 pi, this is minus pi, and this is minus 2 pi, right? This is minus 2 pi. Now if I am simply stretching it, right, if I am simply stretching it, so what will happen? So basically okay, I was just lost in few minds. If I am stretching it, so I will make this sine of 2x. If I make this sine of 2x, what will happen? So for x equals to pi by 2, it will also give me pi. For x equals to pi, it will give me 2 pi. So I am getting more zero crossing points. So it will cross 0 twice as often as previously if my x is 2 pi. So if my x is 2x. So obviously my period will become pi instead of 2 pi. So what do I mean by this? So if I stretch this, right, if I stretch this, this will be something like this. At pi by 4, it will get pi by 2. Let me draw this, then I will explain. And at pi by 2, it will be pi. And here, get this. Right, so the graph will be something like this. Same here also. Obviously the output range won't change this time. Okay, am I doing this correctly or not? So it will cross 0 at maximum point. Yeah, it will cross 0 at maximum point. Then again here, okay. So what is this graph basically? This graph is sine of 2x. Okay, basically the period becomes pi instead of 2 pi, because if I put x equals to pi by 2, what will happen? If I put x equals to pi by 2, this will be sine of pi, which is 0. If I put x equals to pi by 2, it will be sine of pi by 2, which is 1. So it is basically compressing, right? It is compressing. So it is compressing about x-axis, compressing about x-axis. Okay, and if I make this now x by 2, if I make this x by 2, this will elongate this much further. Okay, so what do I mean by this? Basically it will be something like this. You tell me why it will be something like this. So pi by this is pi by 2 to maximum here, right? It will be maximum, and here it will be maximum. Okay, so what is this graph? This graph is sine of x by 2. So you try to explain me why the graph will look something like this. Obviously this is not the exact graph because I'm really bad at drawing, but you tell me why this will be something like this. Okay, next is graphical transformation. So I have y equals to f of x, y equals to f of x. So if y is equals to f of x, now I want to make it modulus, right? Modulus. I want to make it mod. So whatever I have to make it positive. So reflect only the portion below the x-axis above the x-axis. So the portion below the x-axis will be reflected up here, right? Will be reflected up here. Okay. So basically, I just want to make all the negative things positive. Okay, I just make all the negative things positive. Okay. So this will be my modulus of x, right? This will be my modulus of x. Now, if I make x as mod, instead of the whole f of x mod, I just want to make the x mod. So this thing is very interesting. You have to notice to me right now. You have to focus on me. So basically, for this, right, what am I doing? I am ignoring all the negative values of x. That is what mod x does, right? So whatever, like if x is -1, mod x will be +1. If x is -0.1, mod x will be +0.1. So inside this function, only positive values can go. Okay. Inside, let me write this. Inside f of x, inside function, we can only give positive values. Okay, we can only give positive values. Okay, so we can never give negative values. So this information about the negative, right, values of x is lost. Information about the negative values of x is lost. So we can remove this portion, and like, what does this -1 will represent now? If I give my x as -1, it will give me output for x equals to 1, because mod of x, I am giving this -1, feeding this -1. This makes it +1. So I will get the output as f of 1. And what is f of 1? F of 1 is somewhere around here. F of -2 is somewhere around here, because this gets back to +2 only. So obviously these things will be same only. Okay, so obviously I can copy this. Okay, I can delete this part. Okay, this negative portion only, and delete this part. And what I will do, I will just copy this thing. Okay, and this, right, if I can somehow paste. Okay, my battery has been gone. I have been talking too long. Just hold on a second. Yeah, so if I just paste this part, this will be something like this, right? This will be something like this. Yeah. Okay, this has to touch the negative -3. Just hold on a second. This writing. Okay, so this is -1 and -3. Okay, so this is basically the reflection, right? Reflection around y-axis. So this makes it a even function. Here, right, this makes everything positive. this makes everything positive, and this makes it an even function because the information for negative or x is simply lost. I don't have any information about the negative side of x. So that is what this thing is telling, that remove the left portion of the curve. So I just remove the left portion of the curve, keep only the portion of the right of y-axis and reflect it about the y-axis, keeping the original position intact. So I just kept the positive portion of the x-axis and I reflect it around the y-axis to keep everything intact, right? So that will be my answer. So this is my f of mod of x, f of mod of x, right? Okay, so yeah, this is how we solve this. So another way what you can do is, basically you can write this in terms of function, right? So your y dash will become basically mod of x square minus mod of x plus 3, right? So like you can observe from here also, like mathematically, that you will only get this for positive values of x can never be negative, right? X can never be negative. Now another type of graphical transformations are there, which are envelopes. So basically, when I'm multiplying two functions, so when y is equals to x sin x, when y is equals to x sin x, basically there will be envelopes, right? Two functions, one is x and another one is sin x. So sin x can be positive or negative, that's why I have to plot for both plus x and negative x. So this will be simply f of x equals to x and f of x equals to minus x, because x sin x, right, can be positive and negative. That's why I have to plot the two things. So I just my g of x is x, but I have to plot the two things. Now obviously this can always lie in this range only. This can always lie in this range only. This can never go out of this range. That's why these two are called envelopes. These two are called envelopes. So x is my envelope right now, and sin x, right, can only be between those two things, right? As I'm multiplying these two. Okay, here also e raised to power minus x. Okay, so this will be, as sin x is both positive and negative, that's why the two envelopes are, this envelope is basically f of x. This is, let me write this as g of x, not f of x. G of x equals to e raised to power minus x, and g of x equals to minus e raised to power minus x, right? So like these are the envelopes, and in between these, right, this will remain. Okay, that's how we plot these type of function. Okay, this is a method to plot these types of function. When we have two functions in multiplication, one function is oscillatory, so this will be something like this, and I will first draw the envelope of this, the outside one. Okay, outside one, and the oscillatory function will lie between these. Okay, so this is another type of transformation. So I will give you a few homeworks. Okay, MSQ, as this lecture has already gone long, and the next lecture will do all the problems, all the solutions, right, of this thing. So just read the question and try to answer this question. Okay, then this is also another question. Just this is actually multiplication. People might get confused with convolution. This is multiplication, simply multiplication. Okay, now this, right, what is this? This is a composite function. This is a composite function. So you have to understand that composite function, which you learned in the previous lecture. Okay, then here, right, I have given you all the graphical transformations. The graph is given to you, and you apply all the transformations, and then you match your solutions. Okay, this is important. So another assignment homework question I've given you, so where this includes most of the transformations. Okay, so yeah, that is it for this lecture, and in the next lecture I will come with the solutions. Okay, thank you for watching.